All right, 12 o'clock. Let's get started. How you folks are doing? How was your Thanksgiving break? Did you have time to decompress, catch up on all the sleep that you were deprived of? No? That's too bad. We had what, like 5 days? Yeah, I wish it was longer. Oh, my break was pretty uneventful. I know. I was trying to just, get back to my normal self and catch up on some sleep. So probably 2 days out of 5, I was just sleeping pretty much the whole day. Okay, yeah, I about the grade inquiries, they're still past grade inquiries. Yes, I also hit Niha with an email. So let's give them a couple more days. If they cannot get it done, then I will step in and just do them myself. Okay. Can we turn the late days we have left at the end of the semester to extra credit? I don't know. We can certainly discuss it. I haven't really thought of it. Can we do stuff like data structures, check their evaluation participation during lab period, and give extra credit for those participated? Well, I think we kind of, I don't know about data structures, but I think we only give credit for the lab to people who show up. So that, I think, kind of works as their participation credit as well, because if you miss the lab without a legitimate reason, you're just not going to get your checkpoints. So I don't know if we want to duplicate this with even more credit for participation apart from. Okay, I mean the participation for their evaluation. Well, I don't only see their percentage of people who voted. I don't see the names. So we cannot do anything by we cannot really award people who did participate because we don't know who those people are. Oh, okay. I think in data structures they give us zero point 0.5 points during the lab for doing their evaluation. Well, I think that was their way of promoting incentivizing people to actually do those evaluations. So if you want this to be one of the options, I'm certainly for it. Okay, but it would be one of the options. So please go to the submitted post and add this to the list of things that should be considered, and I will certainly include this as an option. But it would be one of the options, not in addition to other options. Is that making sense? Okay. All right, and I see our panelists are here. How's the weather? Cold, too cold? Yeah, it definitely looks like winter came to Troy. So, all right, and let me start sharing something so that we can move forward with our agenda today. That's not it. I want to start it with my notes. And as usual, I need to organize my windows. Chat. Professor, can you just quickly go over the options you gave us for people that haven't checked the discussion forum? Sure thing. So yeah, it's on my agenda. So let's quickly go through it, and then of course you can ask more. All right, somebody actually posted them here. Thank you. And yeah, we can certainly, I can give my comments on any of those. All right, so first, test 6 still being graded. So far, it's looking good. I think we've made some good progress on problem 2, and the average looks pretty good. And I believe our TAs are trying to get test 6 grading done before the end of the week. So, stay tuned for more news. I think that's their current ETA. So, that they are also humans. They also wanted to, to catch their breath over the break, which I think is, very fair considering how hard they have been working for the entire semester, which is not over yet, but, we are almost at the end, right? Believe it or not, we have less than 2 weeks. So homework 7 has already been posted. It's due on December 7th. This is Tuesday. And then there's just one test left on December 8th, our Wednesday. And your last computer organization lab ever is tomorrow on Wednesday, the 1st of December. So that's that for the project. We hopefully all of you are working, so all the groups are working, and we had a mini poll on your favorite group names. I think this is their top 3 one. The list of top 3 most popular, most voted for group names. Looking at the names, makes me a little sad because there are words like pain and suffering, and misery, and especially in relation to MIPS. Don't you think MIPS is very cool? Or did we torture you too much with MIPS? That's probably it. All right. Anyway, by and large, MIPS is behind, right? So there will be no more, additional MIPS stuff. Of course, we will come across MIPS code, every now and then in the remaining 2 weeks. But by and large, we are done with MIPS. All right, and so then Lab 7 tomorrow, it's going to be on the topic that we covered today, cache. All right, so and it's not that type of cache. And speaking of this, it's it's a little digression. So we will be talking about cache memory. How do you spell it? I didn't spell it correctly here. Yeah, it's spelled cache with a CH. Does anyone know why? Where this word is? Yeah, it's not cash as in money. Unfortunately, yeah, it's the other cash. So does anyone know why this word is spelled so in such a weird manner, differently from cash as in money? So it should be spelled with CACHE, with an E in the end and with a CH, not SH. Yes, cash. So anyone knows where cash comes from? Because it gives me headache. Yeah, that's a good one, but it even sounds slightly differently. All right, capitalism. Used to call it catch. That's a good one. C-A-C-A. Yeah, cash. All right, but in seriously, this word is actually borrowed from French, and in French there is a verb, cacher, and cacher means to hide. Okay, yeah, exactly, cache, hide. And so cache can be loosely translated as secret storage or secret hidden place. Okay, so and that's exactly what this word means when we talk about cache memory. So it's like your little secret storage where you keep their values from the memory that you love the most, or when where love translates to their values that you believe are going to be useful in the future. Okay, so we'll talk about more today, but just wanted to mention this you know linguistic little quirk that cache is actually spelled as CHCHE when we're talking about cache memory. All right, and then yes, so course evaluations are open. I believe they should be open until the 11th of December, but you should, all of you should have already received emails from APHIS or whoever manages course evaluations at RPI, and that email should have a date when by which you need to complete evals and the link. So please let us know if you didn't receive that email, or you are if you're having any trouble logging into APHIS or like any other issues. Let us know. We will forward it to the appropriate office who should be able to help you. Right. So we want everyone to be able to complete their evals if they want to. And yeah, so there is a post on Submitted Forum that I made a little earlier this morning, about my ideas of rewarding the class as a whole for higher levels of participation in these evals, because they are important and they actually mean a lot more than you might think for the instructor and for the department and for the school. All right. So yeah, and somebody even posted the link. Thank you. All right, and yeah, so I think it is totally possible to achieve high participation rates, but it actually varies. It varies with the size of the class. It varies with the instruction mode. So it's very hard to predict. If you ask me what I expect, I honestly don't know. In the last few classes that I taught, and they were not Comporg, so they were different classes, we had, with similar incentives for participation, I've seen participation rates, between 79 and I believe like 87%. Okay, but those were, I think, smaller classes than this one. So I don't know if that tells you anything or not, but don't try to project those past results from different classes of different sizes to this class. I honestly don't know what to expect. And yeah, so if you think about it, it's actually a very interesting computational problem. Like, given all their input data, what would be the optimal choice? Like, each of you will need to make a choice, but you are also making a choice as a group, right? So, is there any value in trying to collaborate and came up with some joint decision or some coordinated decision that would maximize their value of this offer to the entire class? How would their utility or the value of that offer compare if you think about their utility for the class in general and for each individual student? Right? It's not a trivial problem. It is actually a computational problem. So feel free to do whatever you want to apply any methods that you learned, maybe in your algo class, right? Or maybe if someone is willing to do some machine learning and look at past um, course evaluations percentage participation rates. I have this data. It's not a whole lot, so probably not enough to really do any machine learning. But if you folks are willing to do anything, anything exciting with this, just knock yourself out. Okay, and yeah, so some options seem very close. Some of them are clearly very different. So we will run a sub-mini poll. So I want to let this submittee forum thread, run for a couple days so that people can suggest additional options. Right? We can include as many options as you would like, provided that those are, like I mentioned in my post, those are reasonable options. Like getting all 7 exams, making all 7 exams optional or extra credit is obviously not an option. So any reasonable options that you might think of that you think would be beneficial to you as a student or to you as the entire class, feel free to comment in that thread, and then in a couple of days I will collect all those reasonable options and add them to my options that I started with, and then we're going to have a poll, right? Because this is such obviously an important thing. I will just make this poll probably on Thursday and let it run for not just for the duration of the lecture as our usual pop quiz polls, but for a few days, maybe until the end of the week at least, so that all people, even people who are not actively attending lectures, have a chance to express their opinion, right? We want to have as many people vote as possible so that we are sure that their option that ends up being selected is really representative of the opinion of the class, and as many people in the class as wanted to actually express their opinion. And so then once this poll is done, we will just go with the highest option, with the option with the highest number of votes, and that would apply for the entire class. So like I explained, there's no way on Submitee we can do any kind of individual, personalized offers. So the offer is going to be the same for the entire class. All right. Yeah, and I see there's a whole discussion about those options. Yes. So as many of you have noticed, some of them are relatively low risk. I think the lowest percentage rate is like 50%, but also relatively low reward. And some of them are much higher reward, but also higher risk because their participation rate bar is a little higher. So, like I said, it's a non-trivial optimization task if you look at it from their standpoint of the students. How will extra credit work with test grade drops? I'm not sure. So extra credit, I believe, is only for their homework incentive. So let's actually let me comment on the options. It should be right here. All right. Well, one option that kind of stands apart is optional extra credit homework. Okay. So, for this one, the bar is really low, 40%. Of course, to compensate for the bar being so low, it means that you would have to do this additional work. Okay, so all other options require literally zero effort. You just select what you want that option to be, and then you just need to do your evals. Right? There's no extra work in the class that you would need to do. In option 6, you get an optional extra credit homework, and there will be no cap. So you can actually, if you're doing well with your homework assignments, then you can still do this homework, and you will score over 100 on their homework category, and it would help to repair your other categories like tasks or labs or whatever you might have, any other category where you might have missed some points during the semester. Okay, but it's only one homework, and yeah, it's extra work that you would have to do, and yes, it's in the last week of the semester, so it's going to be pretty hard, and yes, you wouldn't know, until evals close whether we hit 40% or not. Well, I mean, I can keep you posted, right? So I can let you know as soon as we reach 40%. But if we reach 40% only in the last day of classes, that's it. You would have less than a day to, to make your decision. Or you may decide to do this homework anyway and submit it without really knowing whether it's going to be counted or not, because at that time we might not, be at 40% or more. All right, and so the other options are revolve around the same idea. Let's drop something, right? And so the variables are what are we, what we are dropping, and what their cutoff percentages or cutoff parameters are, right? So for drop their lowest test grades, right? We propose drop 1 for each 30% participation rate at above 60%, right? So if we hit 60, that means drop one test. If we hit 90%, it means drop 2 tests. Then similar thing just for the homework, and since homework assignments are worth a slightly different amount than tests, then the parameters are slightly different. So we start at 50%. So one homework gets dropped at 50%, and 2 homework assignments get dropped at 80%. And then 2 options. There's also similar incentive for lab, and of course labs are worth a lot less. So we drop another lab for each 10% participation rate, starting from 60%. So 60% drop 1 lab, 70% drop 2 labs, and so forth. And then 2 combinations where we first drop the homework and then drop their test, or the other way around. We first drop their test and then we drop the homework grade. Okay, depending on the percentages that we reach. All right, is that making sense? Do you have any questions about the options that I came up with? And I'm just scrolling through the list of message. Oh wow, our chat is very active. What happens if we hit 100% course evals? Well, it depends on the option, right? So imagine you selected option number 3, which means that 80 is 3, 90 is 4, and 100 you get to, 5 lowest lab grades dropped. Okay. So for other, right, it's the threshold is here is 90, and if if we get 100, it's still less than 90 plus 30. So yeah, 90 is really the best thing under this option number 1. Okay, so for now, I would say just concentrate on the options that you think should be added, and then there will be voting as the next step, right? So I just want to make sure that I don't miss any options that you would like to be included, and then you would be allowed to vote for more than one. Okay, so we in this poll you can vote for more than one, and then we just select their option with the highest. With the largest number of votes. Okay, yeah, it's like gambling, but if you think about it, right, gambling is really a mathematical computational task, right? So you just need to assess all your unknowns, and if you did that correctly, then you win, right? You can win, right? If you're good, if you did your math correctly. All right. Yeah, if you know. Okay. Let's. Yeah, I know it's very exciting to discuss about all their possibilities, and I get excited too because I like this. This view of this as a computational problem, and so that's I think that's it. And now we just need to get back to our material. We have a little bit of chapter 4 to finish, and then start with chapter 5, so that you can do your lab tomorrow. All right. So here we are, and we started talking about exceptions last time, but we almost ran out of time, so I wanted to kind of quickly go over this again, and then talk in a little bit more detail about the stuff that we didn't get to discussing last time. Exceptions and interrupts. So an exception is basically defined, and you might be familiar with exceptions from programming languages that you learned, like Java and C++, and Python, of course. Almost all modern programming languages have some kind of notion of an exception. So basically, it's an event that requires a fairly unusual change of the flow of control, right? So, for example, in a programming language, in like your Python or your C++, if you get an exception, then you do not normally return from the procedure or from the function through the return statement, but you return from that procedure function prematurely, and you will be searching for the handler of their exception, and their control will be passed to that handler procedure. Okay, and that concept is very similar when we think about it at the hardware level. So when we have our MIPS and our processor, and we have our instructions, and some instructions might be wrong. For example, think about their instruction memory getting corrupt, and changing some of the bits of the instructions so that the instruction is no longer valid. And the most obvious example is an incorrect opcode, an opcode that does not correspond to any of their valid instructions in our instruction set architecture, ISA. Or another example, an overflow, right? So far, we are ignoring overflow, and we are saying, well, it's the responsibility of a programmer to make sure that any arithmetic instructions do not result in overflow, or if they do, that their programmer kind of handles that in their program. And so those are examples of exceptions, and of course, those are related to what happens inside the processor, inside the CPU. So how do we provide a handling procedure for those unexpected, unforeseen, well, maybe predicted, maybe of course possible situations, but still, situations that we classify as somewhat abnormal. And the idea is the same. We need to have a handler. We need to have some kind of code stored somewhere in the instruction memory that would provide the reaction to an exception when an exception happens. And another thing that can happen, and that in some sense is similar to exceptions, is called interrupts. Right? Interrupts is not something that you would be familiar with from programming languages, but an interrupt is something that is the reality for hardware that runs your instructions, for the CPU, for example. So apart from the CPU, there are other pieces of the system which we were not really talking about. Those are the peripherals, right? Whereas we were mostly concentrating on the CPU. And those peripherals may require attention from the CPU. So, for example, your disk I/O is very slow, and you might want to do it in the background. And then when your disk I/O is done, you want your I/O controller to signal the processor that the data that was requested earlier is ready, it has been retrieved, and it is ready to be transferred to the CPU. So that use case is a typical use case for an interrupt. So the I/O controller would raise an interrupt, basically signaling the CPU that it needs its attention. And interrupt is a physical signal, right? So it might be like just a wire where one means that their external device is signaling something to their processor. So processors would have special inputs for interrupts, or more typically these days there will be a special interrupt controller that would collect interrupts from all their peripherals, and then it can do a lot of fancy stuff, prioritizing them and masking them, and a lot of different stuff. But eventually it will talk to their processor about their interrupts that it received. All right. So So with our MIPS processor, right, we want to decide how their exceptions and interrupts are going to be handled. They are going to be handled in a very similar manner. That's why we then just talk about handling exceptions. Keeping in mind that a very similar process might happen for interrupts as well. And in MIPS, exceptions are handled by a dedicated co-processor, which we call co-processor 0 or CP0, to distinguish it from the other co-processor that we discussed earlier, CP1, co-processor 1, that contains all floating point math and that takes care of all floating point operations. And what we need to do when an exception happens? Well, first we need to store the program counter of their instruction that got interrupted or that was offending because of the overflow or incorrect opcode or any other condition event that caused this exception. And obviously we need a separate register for that. We call it EPC, exception program counter. And we need it because the next thing that is going to happen is we're going to jump, we're going to change the control flow. We're going to jump to the procedure that will be handling this exception. And if we don't save the current instructions PC, we won't be able to come back to that procedure that was interrupted when an exception happened. And usually that's not a good thing, right? Usually at least there are some exceptions that we want to handle and then continue execution of our normal procedure that got interrupted. And so in EPC, we store the program counter. We also need an additional register called cause register because we might have different sources of exceptions and interrupts, and we typically want to know which event happened, what exactly happened. Was it an invalid opcode, or was it an arithmetic overflow? And we store this reason, the reason of their exception or interrupt, in this cause register. Okay, so in the simplest case, it can be 1 bit, but of course it can be more bits. Okay, so in our simplest example, we can let's say assume their encoding where 0 in the cause register means that their exception happened because it was an invalid opcode, and 1 if it was an overflow. Okay, why do we need this? Well, because if we have a single handler that we jump to, then we would want to determine the cause of their exception, and we can do that only by looking at the value of this cause register. So the first example that we are starting with is exactly this. We have a single handler that handles all exceptions and interrupts, and the handler is again the code that that is stored at this address, right? And this address is usually fixed for any given processor, any given architecture, but it is instruction memory, right? So it's just a designated piece, and let's assume that this address is exactly this, right? 8000 and 0180. So I think there's actually an extra 0 here, right? We need to have 8 digits, 8 hexadecimal digits, not 9. All right. So that was one idea. The other idea is, well, instead of having this single interrupt and exception handling procedure that always gets called whenever any interrupt or exception happens, and then it uses the cause register to determine the code, and that can be used to build the conditional logic of that program handler procedure itself. We can have what is known as vectored interrupts, and with vectored interrupts we will have a separate procedure for each of the possible causes, for each of the possible interrupts, each of the possible exceptions. So the handler address will be determined by the cause of the exception or interrupt. And here's an example for a unified opcode. This is the address of the handler that would respond to invalid opcode exception. This is, and it's a different address for the instruction that for the program for the handler that would respond to an overflow event and so forth. Note that the spacing between those addresses is actually very tight, right? It's only 20 hexadecimal, so it's only 20 bytes, right? So, and we know that each instruction is is 4 bytes. So it's not a whole lot of instructions here. More precisely, right? It is 20 hexadecimal is what? It is 2 times 16, so it's 32 bytes divided by 4. So we just have 8 instructions for the handler. And it looks like it's not a whole lot, but we really can treat this address as a vector so that it really contains the jump to the real handler, right? So we can have an additional level of control flow in direction here. And this way we can keep our, this memory area that contains all those addresses very compact. So if this is the case, then we say that's why we call those vectors, right? Because they don't really have their handler procedure itself, but they have a jump instruction that leads to their handler procedure. And then this table here, this very compact table, would be known as their interrupt table. All right. So so there are 2 choices, right? One which we just reviewed, right, when the instructions would just jump to the real handler, and the other one would be when the instruction really contains the handler and it deals with the real interrupt. All right, and yeah, someone is not muted. Could you please mute yourself?
Oh, is it the Demon Slayer game?
All right, or I would have to do it, but it would take me. That person is probably not.
Is it a Pokemon
don't
game?
hear me.
The multiplayer.
I need to come up with.
I'm so. Rocket.
All right, I think I muted them. All right. Sorry about that, but we are back. All right, and yeah, I see that the discussion on the options still goes on. Yeah, I know. It's a sensitive topic, so I don't blame you. If I were a student, I would be excited to. But nonetheless, let's try to concentrate on our material. There will be plenty of time to decide on the incentive. All right, so for the handler itself, then, what does it do? What does the handler do? Well, typically, the handler would determine the cause in case we don't have vectored interrupts, right? Because if we have vectored interrupts, then each cause would get its own handler, so there's no need to determine the cause because it kind of happens automatically. It happens naturally. If we have a single interrupt address and then a single handler, then of course it needs to build some conditional logic by reading the cause from the cause register and then deciding what to do, transferring to the relevant handler or to the relevant part of the handler, determining the action that is required. Action is obviously going to be different depending on the cause, right? If there is an invalid code, we might want to do nothing but terminate the program, for example, or just ignore this instruction that had an invalid opcode. In case of an overflow, we might decide to, do something else, maybe somehow log this problem, or maybe also ignore it. So it depends. And there are 2 cases, right? We might want to get back to the program, to the procedure that was interrupted by this when this exception happened, or we might decide that it's not reasonable to do that. So hence the distinction between exceptions being restartable or not. If we treat an exception as restartable, their general flow is we take some corrective action, and then we use our exception program counter to return to the program that was interrupted. And the other option is if an exception signals about the condition that clearly means the program should be terminated because it is so wrong we should not be continuing, and a good example is probably an invalid opcode, then we just terminate the program. Okay, so we do not return to the procedure that was interrupted when this exception happened, and we might still log the error, so report the error, leave a trace, leave some kind of message somewhere, maybe in the main memory, about what happened, the address that had the offending instruction, the cause, and so forth. But we would not return to that procedure that was interrupted. All right, and so then with a pipelined processor, of course, things are getting more interesting with how exceptions are handled. So we just discussed that exceptions are a form of a control hazard, right? Because when exception happens, invariably we're going to be jumping to their exception handler. And for a pipelined processor, it means that all the instructions that follow the offending instruction and that have been fetched already and that are in the pipeline, all those instructions need to be dumped or need to be flushed, as we discussed this term before, right? We flush the pipeline from the instructions that were fetched and maybe started execution at various stages of execution, but that will end up never being executed in real life because there was this unexpected, unpredicted change of the control flow. So, for example, imagine you are your processor is executing this add instruction, and it results in the overflow. And the overflow we can only detect with our ALU, and ALU is the EX stage. So at that point, when we detect that this instruction caused an overflow, there will be two more instructions already in the pipeline. One instruction being decoded, one instruction being fetched. And obviously, when this overflow happens, we don't want these two instructions to continue execution, so we have to turn them into bubbles. All right. One thing that we need to be careful about when this add instruction with an overflow happens, we want to make sure that it does not write its result back into register 1. So, because that result would be incorrect if we treat overflow as an exceptional situation that signals that the result is incorrect. And therefore, we need to prevent this register 1 from being overwritten, from being clobbered. And that means that we have to turn this add instruction into NOP for the two remaining stages of its execution, right? Because currently add is at EX stage. It still needs to go through their memory and write backstage. So most importantly, we want to make sure that at the write backstage of this instruction, add does not write anything back into the register file. And we want to complete all previous instructions. So all instructions before add need to leave the pipeline normally, and then we flush add and all subsequent instructions because we're going to be jumping to a new memory address. So we want to set the cause and EPC registers, and then we just jump to the exception handler, transfer control to the handler. So it is somewhat similar to their mispredicted branch, so largely uses the same hardware, but with a few little twists and a few additional hardware that we need for the cause register and EPC register, and we need to flush their current instruction as well, not just their instructions that are that were fetched after the current instruction. All right, so here is your pipeline with exceptions, right? Hopefully it's not too overwhelming because most of it should be already familiar to you, but here are a few things that we added related to exceptions. So this is the cause and EPC registers that we discussed, and here is this addition that we need to now provide this address of their of their exception handler, right? So here we assume we're not using vectored interrupts, so there's only one address for all exceptions and interrupts. But when exception happens, we need to be able to jump to this address. So we have to supply it as one of the possible options for what to load into the program counter. So you see how this multiplexer, becomes larger than it used to be. Now it has to handle 3 possible cases, right? We either continue to PC plus 4, or we continue to the address that we get from here for their branch instructions, right? So it would be this lower thing, or we jump to the exception and interrupt handler procedure, which would be this address. All right, and so exceptions. It's like I mentioned, there's a lot more to talk about exceptions potentially, but we're gonna try to stay fairly high level, but exceptions have properties. So there are different, types of exceptions. So we already talked about restartable exceptions versus non-restartable. So with restartable exceptions, when we want to come back to the procedure that was interrupted when the exception happened, it's another change of the control flow. So we want the pipeline to flush the instruction, and when the handler executes and completes its execution, we want to return to their instruction that was that caused this exception to happen, which means we need to refetch that instruction and execute it from scratch. Okay, and so PC is saved in the EPC when exception happens. So actually, PC plus 4 is saved, as we know, because PC adding 4 to PC happens very early in their instruction execution cycle. So most of the time we have PC plus 4 already computed, and that's why when the current value of PC is saved in EPC when exception happens, it's actually not PC but already incremented PC plus 4. So in the handler, we must adjust this value from EPC by obviously subtracting 4, right? If we want our control flow to return to the offending instruction, we want to subtract 4 from the EPC. All right, here is an exception. Here is an example of an exception. It's the same add instruction that we assume causes an overflow because the result of adding the contents of registers 1 and 2 does not fit in 32 bits. And so this is the handler, right? This is the first word of the handler. And note how we just, saving registers into our memory as their first 2 instructions of our handler procedure. And note that after add we have SLT and LW. It doesn't matter what those instructions are, but just remember them because we will see them on the next slide. And also note their addresses, right? So the address of add instruction is 4C. The address of their following instruction is 50 and then 54. So obviously, when we look at the snapshot of our processor, when are we able to detect that we have an overflow in our add instruction? Well, at the EX stage, right? That's why add instruction, right? That's the troublemaker. That instruction is here, and this OR instruction is their instruction before AND, right? So it's this instruction. And then there is another instruction before that. They're still in the pipeline. So those instructions before add should continue execution normally, right? They should leave the pipeline in a natural fashion. This add instruction causes their exception, and we know that their control should be passed to our handler, and our handler is at this address 8000 and then 0180. All right, and then the following instructions, SLT, LW, they have already been fetched right? They follow their add instruction, but those instructions are not going to be executed if we have an exception. So we have to flush those instructions down their, down the pipe. So we should not be executing them, but instead we should fetch an instruction from address 8000-180. And if you look at their values, all right, again, in this diagram, please make sure that you understand where, things are coming from. So for example, why is this $1, $2? Well, because those are the values that are being added by this instruction. Why do we have $6, $7 here? And $6, $7 here refer not to 6 and 7, but to the contents of those registers, 6 and 7, 2 and 1. Well, because this instruction, SLT, is currently at the ID stage, and it is reading those two registers, 6 and 7, and then it will be comparing them. All right, and so if you look at other values, we see that their address of add instruction is 4C, the address in memory where add instruction is located. So 4C plus 4, right? After we have already done plus 4 right here, we're gonna have 50, right? That's the address of the next instruction. So it's not here, because here it's plus 4 relative to the LW instruction, which is at 54. That's why it's 58, right? Because LW is at 54. So 54 plus 4 is 58. The previous instruction would have the previous plus 4 value, which would be 54, and add would have the previous plus 4 value, which would be 50. Right, that's why when exception happens, 50 will be written to EPC. As you can see here, it's shaded because it will be written, so the cause register will also be updated with a 0 or 1. We decided that it's our simple cause encoding, where we just have to distinguish two causes: invalid opcode and overflow. All right, and so when this exception happens, note how this multiplexer and the control signal, the selector for this multiplexer, is not shown, unfortunately, but you can easily reproduce it, or you can easily, make it, just based on other, just based on the flag that would signal whether an exception happened or not. And note how this value actually, so we can see that the multiplexer is in the state where it passes this middle input to the output. So that would be the next value of PC, right? And that would be the instruction that should be fetched next. It would be this SW instruction. And that means that this SLT and this LW will need to be flushed, and their add instruction should also be prevented from making any changes to their state of the system at its memory and write back stage. So effectively, add should be changed to a knob. All right, and so this is their next snapshot, right? So this is their next moment of time and the next clock cycle, and you see how things moved and changed. So please, it's important to see, why these two snapshots make sense and how they, what the significance is. So this AND instruction is out of the pipeline, okay? And this OR instruction is in the last stage, right? So we just moved one clock cycle down the road. So this bubble is our former add instruction that turned into a bubble, so that it is prevented from, updating register 1 at the write back stage. And then this instruction is what used to be SLT. All right, so this instruction is what used to be LW. Okay, those had to be turned into knobs so that they don't execute. And this is the instruction, the first instruction from the handler, from this address that ends in 180, and that is being executed. Okay, and note how all the values have actually moved through the pipeline as our instructions moved. Okay, so you can see, for example, that this address is now 58. Okay, and that was the address of the LW instruction. And here, if we sum this up, the next PC plus 4 would be 8000-184. That would be the next instruction, and so forth. Okay. And I think there is a question: does EPC call and the entire program itself? Then what happens to the instructions before that in the pipeline? Well, EPC is not a call. EPC is just a register. Okay, this is a register. It's like PC, but a saved version of the PC. So when exception happens, EPC gets the value of their instruction that caused their exception to happen. Okay, in our case, it is 50. You see how 50 is written into EPC. And well, as we just discussed, it's not really the instruction, but it's the PC plus 4 for this instruction, right? So the real value for this, the real address of this instruction is 4C. 50 is 4C plus 4. Okay, and it gets written back into EPC, and then their control is passed to the control is passed to this SW, which is the handler. And then the handler decides whether to return to the value, to the address, to the instruction stored in EPC or not. That is the difference between restartable exceptions and non-restartable. Is 8180 before the PC from EPC. 8000 is just hard coded. It's a constant for a given processor. So here it's not programmable. It is a single address for all exceptions, right? So any exception or interrupt happens, the control is passed to this address, right? It's an address in instruction memory, so it contains the procedure that will then read the cause register and determine whether their exception is restartable or not. If it's not restartable, it's just going to halt the processor. If it's restartable, it will perform some handling, for example, changing the values of registers 1 and 2 so that when we attempt to perform this add instruction again, overflow doesn't happen. Otherwise, it's going to be just an infinite loop. Okay, and then when the handling is complete, when the handler is done handling this particular exception, and it's a restartable exception, last instruction in the handler would be JR with the EPC. So it will return to the address of which is stored in EPC. And as we discussed, technically it would be EPC minus 4. So we would first have to decrement EPC by 4 and then do our JR. How does the handler know when it's done handling? Well, the handler is written by their programmer, right? So you, as a designer, you need to determine what this handling is going to be, right? So it's just a program, right? So here, this is just a program, okay? And it needs to be written by someone, okay? It can be given to you when you write your own program and you flash it into their instruction memory. You might be given this standard handler, or you might be required to actually write your own, or you might have a choice, keep the standard one or write your own. All right. So, what else can make our lives more complicated? Well, we might have multiple exceptions. How is that possible? Well, it is possible with pipelining. Okay. So, the example that we gave was with an exception that we were able to detect at the EX stage, the overflow example. However, we might also have exceptions associated with invalid opcode. And invalid opcode we are able to detect at the ID stage. So it is totally possible for this add instruction to have an overflow. And for this instruction, right? It's not going to be this exact instruction, but for the following instruction to have an invalid opcode. And then it will turn out that two exceptions are detected at the same clock cycle. Okay, because remember, this is a single clock period, single clock cycle diagram. It shows a snapshot. It shows what happens at a given moment of time. And we might have the overflow detected for add instruction at the same time as we detect that it's an invalid opcode for the instruction that follows the add instruction. And hence, we have to deal with multiple exceptions at once in the same clock cycle. Isn't that nice? All right, so there are different approaches to that. Simple approach, just deal with exception from the earliest instruction, like with our overflow from an add instruction, and just flush subsequent instructions regardless of whether they are causing exceptions or not. So that approach would be called precise exceptions, because we would always know which exception caused the exception handler to execute, right? Because even if we have multiple, we just ignore others. We only take the earliest one. And in complex pipelines, of course, it can be pretty complicated. It can get really messy with in pipelines with many stages, because there are multiple instructions issued per cycle. We might also have out of order execution, which we will talk about briefly a little later. And where maintaining precise exceptions might be insanely difficult, virtually impossible. So in those cases, we can have imprecise exceptions, right? Isn't that nice? Something imprecise in a digital circuit, where we just stop the pipeline, save the state, and save their exception causes for all exceptions if there's more than one, and let just the handler deal with this mess. Okay, so then it would be the handler's responsibility to see if there are multiple causes recorded, and obviously the cause register would have to be changed. Right, it should now be able to be capable of storing multiple exception causes. So then their handler would analyze all those exception causes stored in this cause register, and decide which instruction to complete or flush. And so it just complicates the handler. But again, a handler is a program, so you can make it as trivial or as complex as you want to be. Right? You want to be more sophisticated, you can write a very elaborate exception handler. So in a sense, it makes the hardware easier, but at the cost of making the handler a lot more complicated. And this approach, and the reason it's called imprecise is because the processor would not know which precise exception happened, because there would be more than one. Yeah, we're gonna have a poll for this class, um, and I think it's coming up. It's coming up. More than one, hopefully. All right, and so for complex multiple issue out of order pipelines, it's not going to be feasible. And we're going to talk about multiple issue in just a few minutes. So, and actually, that's the start of this new subtopic called instruction level parallelism. We not hopefully going to spend too much time on this, right? But there are a couple important things that I want you to know, and there is one specific example that is very illustrative, and that I want you to definitely understand, because it might actually appear, a similar problem might appear on the test. All right, so the idea behind pipelining that we already covered is that we execute multiple instructions in parallel at the same time. So this ILP, instruction level parallelism, there are different ways of increasing this, right? Obviously, we want to increase it, because more parallelism, more efficiency, more better throughput we have. We have smaller in time intervals between each instruction completing its execution. So one approach is to make a deeper pipeline, a pipeline with more stages, because then there will be less work per stage, and we can have shorter clock cycles. I think we've done an example of this in one of the previous lectures. And that, of course, is a good thing, but remember the price that you have to pay or the limiting factor. We cannot really make the pipeline too deep because then the cost of the cost of hazards might become prohibitive. All right, and that of course is you know is the limiting factor. Multi-core processors. No, that's not what we are talking about in this topic. Multiple core processors are coming up in our chapter 6. All right, it's going to be next week, our last topic. All right, so we can do what is known as multiple issue. In other words, if you think about it, what prevents us from, from, for example, executing, from reading two instructions from our instruction memory in the same clock cycle? Well, the only thing that limits us is is that we have a single instruction memory, and so far we were not able to read more than one word at a time. What about ALU? Well, ALU can only perform one, addition, subtraction, whatever, at any given clock cycle. So what if we want two instructions to perform the EX stage in the same clock cycle? Well, we have to throw in more hardware. So we have to replicate pipeline stages, or at least modify our pipeline stages to support even a greater degree of parallelism. So this replicating pipeline stages leads to multiple pipelines. So it's basically like imagine you replicate, you throw in additional hardware to certain stages so that you now have multiple pipelines. Okay, so that would allow us, and we will see an example coming up. If it's a little abstract right now, just bear with me. We will have an example coming up. So we can actually, when we do this, when we implement multiple issue, we would be able to start multiple instructions per clock cycle. This is not something we could do with our previous design, right? We can only fetch one instruction in any given clock cycle, and then that instruction would travel through the rest of the pipeline, but we could not execute two instructions in the same stage of the pipeline in any given clock. With multiple issue, it is now becoming possible. And therefore, we're going to have less than one for the clocks per instruction, right? Because we have more than one instruction per clock cycle. So in this case, instead of talking about CPI, which would be less than one, and which is still, we could still use that metric. There's nothing wrong with it, but just for humans, it might be a little bit more convenient to deal with values that are greater than one, and that's why if we look at 1 over CPI, right? If CPI is less than 1, 1 over CPI is going to be greater than 1, and we prefer for multiple issue processes, we would prefer this metric. It is called IPC, instructions per clock, right? Because now we can have more than one instruction per clock, which was not possible with our earlier designs. So you will see IPC, you know what it is, right? It's the number of instructions per one clock cycle, like two instructions per one clock cycle. And here's an example. We have a 4 gigahertz four-way multiple issue processor. So four-way multiple issue, this N-way means how many instructions we are able to issue at any given clock cycle. So it's 4 instructions at any given clock cycle, and it's 4 gigahertz. So in total, we are able to run at 16 billion instructions per second. So that means that our ideal peak CPI would be 1/4, or if we invert it, right? If we take the reciprocal, then IPC would be 4, right? So that is the ideal, and note how this value kind of matches this, right? So full way means we can have 4 instructions executed per clock cycle. Well, 4 instructions started execution or entering the pipeline per clock cycle, and that would be our ideal, our most optimistic IPC. In practice, we can only do that if these 4 instructions, right? So we fetch 4 instructions and then start them executing in our, basically, throw those 4 instructions into our processor at the same clock cycle. Obviously, this can only be done if there are no dependencies between their instructions, no dependencies anywhere in this group, okay? Because if there is a dependency, we know it's going to be a hazard and it's going to call for a bubble. So those dependencies, they cause hazards and they would reduce their IPC in practice. So in practice, we are very unlikely to see our idealistic IPC of 4, but still it's going to be, usually it's going to be pretty decent. Usually it is worth it. All right, so that's the idea behind a multiple issue, and we can come up with two approaches to designing multiple issue processors, static and dynamic. Static is very easy conceptually, and this is the example that we will go through, and it allows us to have the compiler group the instructions, and those instructions will be issued together as a packet or package or issue slot. Okay, so the compiler detects and avoids hazards, and basically in static multiple issue, it's the job of the compiler to prepare those packages of instructions to be issued together to the processor, and that's why it's called static, right? Because it is decided at compile time, and it's the easier of the two methods, right? So the second one, dynamic multiple issue, is a little more sophisticated because we want this packaging of instructions into packets or into issue slots to happen dynamically as the CPU executes their instructions, and therefore it is now the CPU who is responsible for packaging the instructions. And the compiler can help to a certain degree by reordering instructions, but largely it is the CPU's job to ensure that there are no hazards between the instructions in the same package. And it requires pretty advanced techniques and a lot of additional hardware from their standpoint, from their side of their CPU to do that. All right, and that's why, of course, it's more complicated, and we're just gonna do a very high level overview of this. So another useful technique that is widely used in processors that exhibit instruction level parallelism is speculation. So speculation, the basic idea is we are trying to predict, we are trying to guess what to do with an instruction, what the next instruction is going to do. And that would, if we guessed correctly, that means that we were able to start this instruction earlier, or as early as possible, and then we just need to figure out if our prediction was correct or not. If it was correct, we complete the operation, but basically it's nothing else to be done because we already performed this operation in advance. If not, that becomes a headache because we have to undo any changes that this instruction has made, and that can be pretty complicated, right? So the price for not predicting correctly, for not guessing correctly, can be pretty high, but that's inevitable. We would have to roll back so that we can then do the right thing. All right, and so this speculation is a technique that is common. It can, it can apply to both static and dynamic multiple issue processors. And here are some examples of speculation. We can speculate on the branch outcome, which we have already done, right? So, if the path taken is different, if we mispredicted the branch, we need to roll back, flush the instructions that were already fetched and started executing. We can also speculate on load. For example, if we have a load word instruction, we can, in many cases, read their data memory that is mentioned in that load word instruction. Okay, but it is gambling, right? Because we are assuming, we are making the guess that the location, that data memory is not updated by any prior instruction. Because if it happens, then we read the data memory from the wrong location. Okay, or we fetched the correct location, but the value has been updated. So the value that we actually read is stale and no good, and we shouldn't be using it. Okay, so we have to roll back. All right, so speculation can happen at the compiler or the hardware level. So compiler can reorder instructions, for example, move load before the branch, or include some instructions that would help us to roll back the instructions that should have never been executed. And hardware can look ahead for instructions to execute. So basically, try to look into the future and execute speculatively those instructions, hoping that those instructions would be their real instructions that need to be executed. So the results would be buffered, and if our speculation was correct, those results would be ready to be consumed from the buffer. If the speculation was wrong, we would have to flush those buffers and start executing those instructions from scratch because we just didn't guess correctly the first time around. And of course, things are getting more complicated if there are exceptions. Yeah, we're not gonna talk too much about it, right? So obviously, we either have to add additional instructions to kind of defer the exceptions, or we need to buffer the exceptions until their instruction completes execution, which may or may not occur. All right. So again, this is speculative. All right, and here this is the start of the example that I want you um, to be familiar with. So static multiple issue, a fairly simple case where we rely on the compiler to group instructions into issue packets or packages so that we are able to execute more than one instruction at a time or start executing more than one instruction at a time. So that means that we need to first define how many instructions per packet we're going to have, and in our example, it's going to be 2. And then we need to decide which instructions to package. Like, can we package together any instructions, or just have a more limited but actually easier to implement mechanism where we only allow instructions of certain types to be grouped together. So that's the other decision, and we will see how it is done in this example. But if you think about this packet or package that contains 2 instructions, you can actually treat it as a single longer instruction, right? So instead of thinking of one instruction at a time, you can think of pairs of instructions. So you can almost think that instead of issuing one 32-bit instruction, we will now be issuing one 64-bit instruction, which contains not just one action, but 2 possible actions, right? But conceptually, you can think of this as very long instruction word, VLIW. All right, and then of course the compiler must take care of all the hazards. So because it's static, multiple issue, the CPU would just blindly execute the instructions, and therefore it will not be able to detect or fix any hazards. So it has to be the compiler's responsibility under static multiple issue. Under dynamic multiple issue, it's going to be the CPU's responsibility. So it means that the compiler should strive to reorder instructions into issue packets such that there are no dependencies between the instructions in the same packet. And if it's unavoidable, if inevitably there are some dependencies between instructions or we cannot reorder them, then we need to we need to have just one instruction in the packet, one real instruction in the packet, and then use NOP for the other instruction. All right, here is their example. And we are trying to make it very simple so that there's a 2-issue system, right? When we say multiple issue, this multiple is 2, which means that there are just 2 instructions per packet. And we place limitations on what the first instruction could be and what the second instruction could be. So we say that the first instruction in the packet must be an ALU or branch instruction, and the second instruction in the packet must be a load or store instruction. And since we have 2 instructions, so effectively it's a 64-bit instruction word, so VLIW, and so we perform ALU branch instruction and then load and store. So first instruction is executed first, second instruction is executed second, but we want them to actually execute in parallel, which means that we need to make sure that there are no dependencies between those instructions. Okay, in other words, ALU branch instruction should not write to a register that is read by load and store. Otherwise, of course, we would not be able to execute those instructions concurrently in parallel. And if it's not possible to avoid such dependencies and we are unable to reorder instructions without changing the semantics of the program, we have to resort to keeping just one instruction, one real instruction in the packet, and then using NOP for the second slot in our package. So here's an example, and we have our ALU branch load and store, ALU branch load and store. So in this case, it's very nice, and we clearly see how we could package them into two, assuming that there are no dependencies, and see how uh, these two are actually handled as a single instruction. They are fetched together, they are decoded together, they are executed together. So essentially, this is like one mega instruction or one VLIW instruction, and then that would be the first packet, and then the second packet would be this pair of instructions. Which would fetch at the same clock cycle, decode at the same clock cycle, and so forth. Of course, the second packet has to be delayed relative to the first one by one clock cycle, right? But we can see that now we have those pairs, right? So that's the idea. And of course, in real life, you're not going to have this perfect ALU load store, ALU load store, ALU load store. So you would have to be creative as a compiler, right? So in this example, you would need to think as a compiler when you are packaging or how you're packaging instructions. So which additional hardware do we need to add to our processor to support this dual issue, right? This static dual issue, this static two issue processor. Well, we need to make sure that our instruction memory can now produce two words at a time, two instruction words at a time. So add consecutive addresses, right? So that's why the address is still the same, right? But it will read not 32 bits, but 64 bits, two instruction words. And then obviously we need to extend our register so that register file that it supports reading not two, but four registers at a time and writing not one, but two registers at a time. So you see how those, and in this diagram, to make it more confusing, they use blue to indicate the additional stuff that needs to be added. So previously blue meant control signals. No, not in this figure. In this figure, blue means the additional stuff that needs to be added. Note how we need to replicate the assign extend module, how we need to replicate the ALU, because we have the potential of two instructions executing. One is ALU, right? So it might be adding something, so it would be using this ALU, and the other is load or store, and it might be using ALU to compute the address. And since now they are executing in parallel, we need to throw in the second ALU. Okay? So that tells you the additional hardware, this replication of resources that we have to provide for our processor in order to support multiple issue. And of course, when there are hazards, we cannot execute instructions in parallel. So if we are able to mitigate hazards with forwarding, of course, we should attempt to do this. So recall that forwarding was avoiding stalls with a single issue, but now we cannot use ALU result in load store in the same packet. So something like that, right? See this dependency here is not going to be possible, right? Because it is the same. It is the same value, and these two instructions execute at the same time. So they have to go into two different packets. We cannot package them in the same packet. We are moving so fast. Yeah, I know, but bear with me. So hopefully it is still making sense, right? And we still need to to talk about their caching, right? Because that's your next lab. All right, and then so load and use hazard. That's it right here. Uh, well, this is not load and use, right? This is just on the same register from arithmetic and load instruction, right? But for it is conceptually very similar to our load use hazard. And previously, it cost us one cycle of the delay, one cycle of their bubble, and now it's two instructions, right? Because we have to, if we are thinking about packing these two, right, we would have to have this add and knob in the first packet, All right, the first packet, and then in the second packet, we're going to have nop and a load. Right. So see how instead of losing just one instruction, we have to lose two instructions, right? Because of this dependency. It's still going to be one clock cycle, right? So that doesn't change, but it's one additional NOP here, right? A NOP is always a loss, right? NOP means a real instruction could have been executed here, and now we cannot package them together, right? Remember, the first instruction must be ALU or branch here, and the second one in our system, right, in the example that we are reviewing, is load word. So we cannot have load word here, right? We have to have it as the second load as the second instruction. So all that means is that the compiler has to be pretty aggressive with scheduling and pretty aggressive with reordering instructions. So here's an example of the scheduling. Note how for the first one, yeah, we have no other choice but put a NOP here and then use their LW as the second instruction. But then we can, play some games with reordering. So, this add U here, right, would not go well with their SW because of this dependency, right? So we want to kind of spread them apart, and so what we do is we move add I in here so that we can have this add I here, and yeah, we don't have a matching load store, but it's okay, it's pretty inevitable. And then we have add U with a NOP, and then we have our BNE with an SW. Okay, so see how we rearranged our instructions so that we can package them in fewer packages. So we only had to make 4 packages, whereas if you make a straightforward, if you follow a straightforward approach, right, you would have one package here, and then you would have one package here, and one package here, and one package here, and one package here. So you would have 1, 2, 3, 4, 5 packages, and we were able to pack it into 4 packages, which is good. So why do we know it's good? We can compute what is our IPC, right? So it's not one. One would be pretty bad, but we have more than one because we have 5 instructions, right? So this 5 is the number of instructions, and this 4 is the number of clock cycles, which is the same as the number of packages, right? So see, the last cycle is 4, so it's 125. Or we could have potentially achieved the IPC of 2 if all our instructions were no dependencies and we could pack them tightly in our packages, right? If we didn't have to insert, to use those 3 NOPs, we would have not 5 instructions, but 8 instructions in 4 packages, and it would be 8 over 4. 8 over 4, that would be IPC of 2. All right, but in this example and in most realistic examples, it's not really feasible. All right, so and then another technique is loop unrolling. So we replicate the loop body so that we can expose more parallelism. We use different registers per replication. So this technique is called register renaming. And one thing that why add I is moved to before the SW? Well, because we are trying to put something between add U and SW, because otherwise they have a dependency that would force us to perform to make a bubble to stall the pipeline. Okay, and by separating them out, the add U and SW, they are now in separate packages, so we were able to avoid it, right? Because otherwise we would be tempted to do add U with the same package as SW, and that is not possible, right? We cannot have them in the same package. No, it's not working, because yes, they happen at the same time. 2 instructions, they happen at the same time when we execute them. But wouldn't it change the value in $1? Well, $1 register. You mean S1? Yeah, S1. S1 changes here with add I, and it is used in here. So it is fine because it is set here, and it is only read here. Okay, SW also uses S1. Yeah, sure. So if you know it's S1 and S1 here, it's fine. Here, oh, you mean like here? Okay, but no, neither B and E, no SW write to S1. So yes, they both use S1, but they read both BNE and SW read from S1, and you can read, several times concurrently the same location. It's fine. Reading is never a problem. Writing, that's what messes things up. Does that make sense? All right, and oh, we have about 20 minutes left. All right, so I would say let's pause our chapter 4 material here at loop unrolling, and let's go through the stuff that you will need for your lab, and then we will come back with more on Friday. All right, so we are starting chapter 5, and so there important observation here, and like why are we talking about memory? Because a memory tends to be the component that is very tricky because you cannot get a lot of memory that would be fast and cheap at the same time. Okay, and that forces us to make very tough decisions. Why do we care if we can access, the amount of time we spend accessing memory locations? Well, that's because you've seen all our data, except for what fits in our 32-bit, 32 general purpose registers, is in memory. So memory load and store operations they constitute a significant fraction of their time that is spent. And if you think about it, it's really wasteful, right? If we could have unlimited memory in the processor, we could just have all our data in the processor, in the registers, and not have any data memory, and that would be so much better. But unfortunately, that's not a realistic expectation. We cannot have a large memory that would be cheap enough to afford it to be placed in the register file. And the other observation is, well, there are cases when we repeatedly access the same location, and we want it to be available for us in the future, so that we don't have to access it again because data memory is slow. And that what drives this idea of the hierarchy of memories. And behind that is the principle of locality, which says there is temporal locality and there is spatial locality. So temporal locality is saying that there is a certain degree of possibility that an item that we accessed from the memory in the past will likely be accessed again in the future. And there are multiple examples. For instance, think about the body of the loop, right? So memory is also instruction memory, so you need to fetch those instructions repeatedly, and they're the same instructions if you execute the body of the loop multiple times, or induction variables, or any such values. So that is temporal locality. Temporal means related to time, right? So, and that's why it's temporal. We accessed it in the past, and we expect it to be needed again in the future. And spatial locality is just a different dimension of this, and it is related to space, right? Spatial means related to space. So items that are close to the items that we accessed in the past are likely to be needed in the future. And a typical example is an array, right? So you have an array in your data memory, and you access this element, and you know that there is a high possibility that in the future, maybe next iteration of the loop, you're gonna need this next element and the next element and the next element, right? So it's spatial locality. You expect the nearby elements to be needed in the future if you accessed a particular element in the past. And the same with sequential instruction access, even to a greater extent, right? Unless you have branch instructions or jump, you read locations from memory sequentially, one by one. So you might predict which location you will need in the future based on the location that you are accessing right now. Okay, so we can take advantage of the locality by building a memory hierarchy where we use memories with different cost speed ratios. So, for example, we can take the largest available memory, which would be disk or some flash memory drive, and which gives us a very low cost per byte of value stored, and store everything there, and then copy their values that of course disk is extremely slow by computers terms, and so we want to speed it up, so we can copy recently accessed that is referring to temporal locality, or nearby items that refers to spatial locality, from the disk to our smaller DRAM memory, which is more expensive per byte of storage than disk, but which is also much faster. Okay, and then so that would be our second level of the hierarchy, which we call main memory, and then we can have even faster memory called SRAM memory that we can only afford fairly small amounts, but that memory is a lot faster than DRAM. And we can copy the even more recently accessed or more nearby items in this SRAM. Typically, SRAM is the memory technology that is used to implement cache. All right, and so thus we can build their hierarchy of levels of the process of the memory, where we have this, our processor at the top. It has very limited register file, very small, and then we can have our next level of the hierarchy, which offers more memory, but which is more expensive. That's why we can only afford a limited amount, and then we can have another level of hierarchy with even more space because it's cheaper, but it is also slower. All right, and so when we copy things across the levels, we only copy from one level to the other, never across their levels. And we only copy if it is necessary. So if access data is present in the upper level, we copy it, right? If not, we retrieve it from the lower level. So term hit refers to the access that is satisfied by the upper level. The value from the address that we wanted is stored in the upper level. And of course, our success rate would be characterized by the number of hits divided by the total number of accesses. And conversely, if the value that we wanted is not in the upper level and we have to go to the lower level, it's a miss, and we can compute the misses per total accesses, or miss ratio, and it would be obviously 1 minus hit ratio. All right. And memory technology over drives, which are very cheap, but which are the slowest. So our ideal memory would have like the access time of SRAM, but the cost of disk or flash drive in terms of the cost per byte or cost per gigabyte. And of course, it's as anything ideal, it's not a realistic expectation, right? So that ain't gonna happen. So we have to combine different memory technologies to produce a reasonable, the system at a reasonable cost. So, and that calls for multiple technologies, memory technologies in the same system, and that in turn hierarchy of memory. Technology I'm not even talk about, so please feel free to read their textbook for more details if you're interested. And of course, none of their slides that I'm skimming through is going to be on the test. All right, so all their stuff from here and up to here, all right, and disk storage, right, and flash, and details of disk sectors and access. So I'm going to just skip through this. All right, so now we are getting back here. So this is the stuff that is important and that might be on the test. So cache memory is the idea is that we have this very fast SRAM memory very close to the processor, right? So it's the next fastest thing after the register file, which is part of the CPU. And if we have a series of accesses, so x1, x2, and so forth, those are addresses. And we want to know, if our instruction calls for accessing, for example, reading this memory location x1, we want to know where to get it. Do we have to go to our main memory with this, or do we have to go to our cache? Where is that value stored? And the rule of thumb, which we mentioned previously, is that the processor only talks to their nearest level, which would be the cache. And if the value happens to be in the cache, it is served from that cache. For example, this xn that we are requesting, you see it's not in our cache memory right now. And what happens? Does the processor go to the main memory and to request this xn address? No. It is the responsibility of the cache. Okay, so cache will get this value at address xn from the memory, from the main memory, from the next lower level memory in our memory hierarchy, and it would store it in the cache. So it would find the place to put it here in the cache itself, and then it will serve it to their processor. So the processor only talks to their cache. The cache then might need to talk to the data memory if it needs to actually retrieve that value. And if after that, if we have item C where we reference xn again, then in this case, their access operation would be satisfied from the cache because we see xn, the value from memory address xn, is already in cache. So cache wouldn't need to talk to data memory in order to satisfy this access request. And their easiest way to organize the cache is a so-called direct mapped cache. This is what you will need to do in your lab tomorrow. And their direct mapped is called that way because the location is uniquely determined by the address of the memory we are trying to access. So there's only one choice. There is a direct correspondence between the address in the memory and the address in cache where that value might go. Of course, cache is much smaller than our main memory, right? If we could afford the cache of the size of our main memory, we wouldn't need additional levels of memory, right? We would just use our main memory if we could afford it to be all SRAM. But if we cannot afford it, which in real life we cannot, we have a cache which is much smaller. So you see how here cache is much smaller. If we want to be precise, it's 4 times smaller than the main memory shown here. And that means that there will be, for every slot, for every line in our cache, for every block in our cache, we will have a competition of between 4 memory locations that map to this cache block, right? So look at this blue thing here, right? You see that there are 4 arrows that go into that blue line of cache from blue addresses of our main memory. Okay, so that means that, well, how do we determine the address? Well, it's very easy, right? We look at the difference between those memory addresses, and they all end in 0, 1, which means, oh, okay, whenever the address of the main memory ends in 0, 1, it would map to, well, not 0, 1, 101, sorry, 101, right? We need 3 bits for this, right? So it would map to cache with index to cache block with index 101. All right, so that means that we are just using a certain number of low order address bits as the index in our cache. So what is the procedure then for, how do we work with the cache? The processor the processor fetches the instruction references the memory, we compute the address of the memory, and then we look at the lowest 3 bits here, and that determines their cache address. All right, then we use these 3 bits to go into the cache. How do we know which address is actually used? Which of the 4 possible options? Well, that calls for additional piece of information here, which would be called the tag. Okay, so how do we know which particular block is stored? We need the tag. All right, so this is the tag. And those are the high order bits. All bits other than the bits that correspond to the index. Is there anything else? Turns out that yes, we need to know if their cache location is actually valid or not, because maybe there is no real data stored in this location, right? Maybe we never requested any of those blue addresses, so this blue block of cache contains just some junk, right? Some values that randomly happen to be there. It hasn't been ever initialized to anything. So we need this additional valid bit to tell us if the value is present, if the cache block has a valid value or not. And of course, initially the value is 0. Okay, and here is their pop quiz. So I believe it's this one, and we will get to the one that I'm skipping because it's in the last part of chapter 4. So we'll get back to it. All right, so let me, it should be, check, it should be that quiz. All right, and here is, and we have 2 minutes left. All right, perfect, to go through this cache example. And in my notes, I'm also giving you a link to a simulator that you could use when learning about caches, right? Cache memory, right? So this is a simulator, online simulator. You could also use MIPS. There is a data cache simulator in MIPS. They look slightly different, but they are pretty much the same. All right, so this cache that we're reviewing, it has 8 blocks. So the size of cache is 8 blocks. There's only 1 word per block, and we will see that you can actually have more later on, but for now it's 1 word per block, and it's direct map, the easiest organization of the cache. Initially, the valid bit is all zeros, right? Because and tag and data, they do contain some values, but it's just some junk, right? It is whatever happened to be after we powered on our system. So we want the valid bit to be 0 or no or false to indicate that, yeah, whatever values are here are not yet valid. And then we are executing an instruction that references address 22 from our memory. This is the binary address of the memory. And is it a miss or a hit? Well, it's a miss because we take the 001 110. This is the index for our cache, and we find that initially it had an n here, so there is no value stored in this block of our cache. So what we do is we read the data from our main memory. So now it contains the value read from this address, and the tag is the 2 most significant bits of the address because we use 3 for their index. And now we switch this valid bit to yes or 1 to indicate that yes, now this is a valid value, and it contains value from address 10110. So if we ever have this reference to word 22 again, it would be served from our cache. And then we do their next instruction, which accesses 26, and 26 maps to this index here. And we do the similar thing. So tag is 11 because this is the tag, goes in here. And now we have two elements of our cache in the valid state. And then if we access this 22 and 26 again, it's going to be a hit because the values are in their cache already. All right. And then if we have 16, right, note that it maps to this index, all zeros, and it's a miss because previously it was not a valid location. So we had a miss, and we brought this value in from our main memory from address 140. And then for number 3, their index is 011. It's here, right? And it's again a miss because we did not have that location valid. So it was N for valid. Now it's yes for valid because we brought that value in right here. And then when we have 16, right, it's a hit because we already have this location cached. And finally, when we have 18, something interesting happens. It's a miss despite the fact that we have yes here, right? So for 18, it's 010. That's the index. We already have something at that index and it says it's valid, but the tags are different, right? We have something with tag 11, but the two most significant bits of this address is 10. So we have the value cached, but it's not the value from the memory location that we need, because remember, there are 4 addresses that compete for this single block of cache, and we don't have the one that we need cached here. That's why it's a miss, and we bring in our value from address 18 here, and it replaces the value that we had before, so we now have 10 as the tag here. All right, so that's that, and that should give you enough information to get you started with their lab tomorrow. And with that, sorry for delaying you by 3 minutes, but we needed to cover this material for the lab tomorrow. So I'm done. I will answer. There are a couple questions. I will answer them in a minute for those who can stay extra couple of minutes. And to all of you, enjoy the rest of your day. And you know, just stay well, stay healthy, and yeah, hopefully the lab tomorrow is not too difficult. And yeah, I'm looking forward to meeting you all on Friday. And please start working on your evals. All right. Thank you so much. Have a good day. And now let me answer the questions that I might have missed. But multiple addresses can map to the same cache location. Yes, this is inevitable because otherwise we wouldn't be able to have a cache which is smaller than their main memory, right? And we are forced to have their cache smaller than main memory because otherwise we wouldn't be able to afford it. That's why we have multiple addresses from the main memory that basically compete for the same cache block. That making sense? All right, and hash table, but in C, yeah, it's somewhat close, but in hash table you can actually have more than one value stored, right? So you can have a linked list and store multiple values in a hash table. Here you can only have one. So if you want to bring in a new value, you have to put it in the spot where the previous value was. So you would overwrite the previous value. You cannot have multiple things that map to the same location in the table. All right, so those are all the questions, I think, or at least recent ones that I was able to get from the chat. And with that, so let me finally say thank you and see you next time.
Sorry, do you
Yeah,
mind
go
answering
ahead.
some questions? Okay. So
Sure.
I'm currently working on the homework right now. Is there any like test cases that we have for the homework? Because I
There
don't know
will.
how I don't know how the format's going to be. Like, they give us a table with, sorry, hold on. I have to look at it. They give us a table that tells you the instruction, the input symbol, and the op bits. But I'm unsure of like what we should do entirely. Given the instruction input symbol, like should we read in the symbol and like have
Okay,
uh
that's a reasonable request. I will post some examples. I will add them to the course materials section.
okay.
Okay, that's a very reasonable request. I probably should have done that before, but thank you for reminding me. I'll
Um
definitely do
I have
that.
a lot of other questions. I don't know if you mind answering. Um
Um, I don't mind. So yeah.
okay. So in the homework, you're not allowed to use a ripple carry header, which makes sense, right?
Yep.
But in the diagram for the carry look ahead unit, it uses an ALU that takes 8 inputs from A0 to A 3 and B0 to B3, which should be like a ALU 4. How should we go on and develop the ALU 4? Because wouldn't we need an adder 4 in order to calculate the values in the ALU 4?
Okay. Let me open up the diagram. So it's improving our ALU in 3B. Okay, so the diagram you are talking about is all right. So there is an ALU which is a 4-bit ALU, right?
Yes.
Okay, so you would need to design it as well.
Okay, so you need to make the 4 ALU, and you
Yes.
can't use like a ripple ALU, right? You can't like connect all the
No,
ALU.
because it would be a ripple carry ALU. So
Okay.
you can totally use your 1-bit ALU or 1-bit adder, whatever you happen to have, right? But then you need to combine like your 4 adders in a manner that would be consistent with their um, carry look ahead. So apart from those 4 single bit adders, you would need to, which each of those adders would have C in and C out, but you don't connect them one to another in this daisy chain manner, which would be ripple carry. But you need to additionally generate those CIs based on the formulas for the carry look ahead.
I get it, but if you're using an adder 1, don't you have to add another like 4 um chains of adder 1s if you want to use an ALU 4?
No, you just use 4 adders, single bit adders, but then you have additional circuitry that produces those C1, C2, C3, and you feed those C1 into the relevant single bit
Okay.
adders. So that the basic idea is those 4 single bit adders should get their C ins more or less at the same time, except for the very first one, right? But the remaining 3 at least should get their C ins at the same time, not one from another, so that the last one in the chain gets its C in their latest. But all 3 of them should get their C in at the same time, because it would be determined by their latency of the gates in this additional circuitry that generates a C CIs from propagate and generate signals.
Okay. It just looked like when I added all the adder ones together, it looked like a ripple carry adder. Like it looked like a chain. So I'm not completely sure.
Okay, well, it shouldn't be a chain. And the way you can tell, if you see that a carry out from one adder is connected to the carry in of another one, it's a ripple carry. And
Okay.
that's not what you want for this homework. But if you see that there are carry ins for your single bit adders, getting their values from this additional circuitry, the gates that implement the carry look ahead thing, then that's the right thing to do. Okay. And yes, they will be different. So, you will have C1 and C2 and C3. Okay. But they should be generated according to the formulas for the carry look ahead thing. And that would, they would be referring to generate G's and P's, not from their carry out output from their previous 1-bit ALU. In fact, if you think about it, one way to kind of check yourself is you will not have anything connected to C out of your single bit adders.
Okay.
Right, because C outs would just be not used because you would generate those C outs with an additional circuitry and much faster than the C outs from a single bit from your single bit adders. Is that making any kind of sense?
Yeah, it makes a little bit more sense, but I have to understand. I need to like go back and think about it.
Okay, yeah, and feel free to get back and ask me more questions or ask on the Submit forum
Okay.
or ask tomorrow during the lab. So
Do you have I have one last question if you don't mind answering.
I'm okay if other
Okay.
people are okay with that. I'm
Actually, I
fine.
might have two other questions. Like the class that they want to look at, what's it called again? The course evaluation, like the state, like what's the percentage right now? Is it possible?
So we have, I think we have like 4 sections of this class, and APHIS reports their values separately for each section. Of course, I will be just combining, all their numbers, adding all the numbers together. But as of this morning, it was like pretty low. So I think in one section it was 11%, in another section it was 9%, in the third section it was 3%. In the fourth section, I don't even remember. But
Okay.
that doesn't really mean anything because that was before most people read the announcement. So we really have to give it a few days and see how we are doing. And I'm pretty certain if you have a minute, I can actually look it up and tell you what we have right now as we speak. And it's loading. It is loading. So we have 6 and 8, 14, and 5, 19, and 1. We have currently 20 people who responded to course evaluations out of, I need my calculator, sorry. So we have 54 plus 73 plus 57 plus 29 people and across all 4 sections. So we have 213 people and 20 people responded. So as of right now, we are a little bit below 10%. But again, that doesn't mean a whole thing because we still have 11 days, and we will only count our chickens when they hatch. So when evaluations close, that's when we determine what the final percentage is. Is that making sense?
Yeah, I got it. It's just a staggering low amount of people that I thought would do the course evaluation.
I see what you're saying, but I think it's too early to say because, as someone else noted, um, not that many, relatively not that many people attend lectures synchronously, right? So we typically have like 60 people, and then some people are just busy with their classes. They want to take their time filling out their eval, so they might do it They may do it later today, tonight, and yet there are even more people who are like, all right, I want to really delay my evals because I want to, see how test 7 goes, and if I'm happy with test 7, I'm gonna give better evals. If I'm unhappy with test 7, I'm gonna lower, I'm gonna ruin his evals. So some people are like that, and they want to get to the very end of the semester, uh, before they file their evaluations. So, but again, like for us, it doesn't matter when people submit their evals. We will take all the evals that are submitted during the entire window that RPI gives you folks to submit your evaluations. So you still have time, right? Yeah, you need to make this decision now, more or less now, within the next few days, about which option you want to go with, without knowing the what the outcome is going to be. So it is a little like betting or gambling, but that what makes this an interesting optimization problem, because you have to make a decision without having without possessing all information. And it's unfortunately it's inevitable, right? We cannot wait until the semester ends and then say, hey, what you folks want to do, because the idea is that we use this incentive to push people towards filling out their evaluations. So we have to do it now while the evaluations are still open. Is that making sense?
Yeah, I got it.
Yeah, and someone says that the stat means literal nothing. I agree. It means nothing at this point. It's too early, and like I said in my previous classes, when we were offering that kind of or similar incentives, and you can actually ask. There are some people in this class who took other classes with me, like in the summer or last spring. Then typically and you would see, like, especially towards the end of the semester, like you would see other students going like, oh, did you fill out your evals? If not, please do. So students are asking other students to actually do those evals. So, and we were able to get to 80% and above. So I'm not saying it is guaranteed to happen, but I think it's quite possible to go above 80% for sure. If students are responsive, and if other students are active as well, asking on Discord, on during labs. I think I saw a discussion in the chat regarding, like, yeah, can we have TAs announcing their or giving people like 10 minutes to fill out their evals? Sure, that would be a good thing to do, I think. So definitely, all means, work. So I'm pretty optimistic. I don't know if that is justified or not, but I'm pretty optimistic.
Okay. Going back to the homework,
Mhm.
because I love the homework. I thought of a different way to develop a carry look ahead unit by using, I think, the something called a carry look ahead cell,
Mhm.
which takes the end of A and B as the generates, and it takes the OR of A and B as the propagate, and it takes the sum of uh, an XOR of the carry in, the A and the B as the sum, which works for an n-bit carry look-ahead adder if you connect all the carry look-ahead cells in kind of like a ripple-like fashion, kind of like an adder.
Okay, it's kind of hard for me to visualize the circuit or the formula that you're describing. So if you don't mind sharing what you found on the forum, you can do that. If you're just sharing, like, the description of the method, it's fine, right? As long as you're not sharing code.
Yeah.
Sharing code is not forbidden. So if you are comfortable doing this on the forum, it's fine. I can look at that later and respond, or you can just send me an email with like your formulas or your circuit. I'm kind of a visual guy, so I prefer really a circuit, and then I can tell you what I think. So there are other methods, of course, for sure, and I'm fine with any variation of the carry look ahead as long as it is not worse in terms of the latency than the carry look ahead that we discussed in class. So when you say that you connected in a sort of ripple carry, that makes me a little worried. That's why I want to see and compute the latency, and you can compute the latency yourself. Think about our test 6, right, where one of the problems was to compute the latency of their carry look ahead, but we gave you the latencies for their for their 4-bit ALUs. In this homework, you would have to design your own everything, and therefore you would be responsible for computing your latencies for everything. And if your total latency for the whole thing with the carry look ahead is no worse than what we would do with the standard formulas from the textbook, then I'm fine with it. But
Okay.
if it's worse, then of course the question would be like, why bother if it's not giving you any advantage? Is that making sense?
Yeah, okay, I got it. So if I email you like a circuit that I made and calculated like the latency for,
Yeah,
that
so
would be much
just
better.
yes. Send me the circuit and your thoughts or like your explanation. And if you so you mentioned that you came up with this. So if you came up with it yourself, then it's fine. If you look it up somewhere and you can reference the source, that would be even better. Like if you got your idea from from reading something in the textbook, or well, not our textbook, right, but some other textbook or on the internet, then just give me the reference so that I could also read the source that inspired you.
Okay, thank you.
You're welcome.
Cat, that's it.
Okay.
Cat.
Well, yeah. Have a good one.
Thank you.
You're welcome. Any other questions?
I just had a quick question.
Sure. Go ahead.
I'm not sure if this was already answered or not, but next week I have exam for this class, Fox and differential equations on the same day. I'm not sure what can be done about that or not, but I don't know.
Send an email to CS1 Comporg instructors mailing list, and we will offer you a makeup. So 3 exams. No, we don't want anyone to go through that. 3 exams on one day. So we will offer you a makeup, and then you will talk to Cheyenne Halbert about their specific day and time.
Okay, cool. Thank you.
You're welcome.